Hi, my name is Hannah, and today I'm going to be discussing Lab 3, Magnetic Field of a Bar Magnet. To introduce the experiment, a couple concepts we will be discussing include distance dependence and Biot-Savart law. The purpose of this experiment is to observe and collect data on bar magnet magnetic fields to determine the distance dependence as well as the magnitude of the magnetic moment. The results for the experiment ended with a distance dependence equaling -2.688 and a magnitude of the magnetic moment being 3.65 am squared. To address the two concepts in this experiment, first I will discuss distance dependence. Distance dependence shows that the magnetic field of a bar magnet falls off with distance. This is summed up in the equation B bar is equal to Kr to the n power. The magnetic field magnitude also is based on the dipole moment of the magnet and is represented by the equation second on the screen. A few assumptions were made during the experiment. First is that the x-axis points along the width of a phone, the y-axis points along the height of the phone, the z-axis points out of the screen as well. Lastly, the magnitude of the magnetic field is proportional to a constant times a power of distance. This experiment was also completed using a magnetometer app and data tracking and interpreting from the data on the app. To go deeper into how this experiment was completed, the magnetometer was used along a yardstick in order to measure the distance away from the bar magnet to see how this impacted the data we were collecting. This data was collected in a spreadsheet which then was able to give us the natural log of bx versus the natural log of r. Once the graph had created the equation y equals -2.6878x minus 14.13, the distance dependence and magnetic moment equations could be applied. The natural log of bx absolute value is equal to n times the natural log of r plus the natural log of k is going to be the same thing as the y equals -2.688x minus 14.13. This means we know that n is equal to -2.688, which is our distance dependence. We also know the natural log of k is equal to -14.13. From there, we know that the absolute value of the b bar is equal to kr to the n power, which is also equal to mu naught over 4 pi times 2 mu over r cubed. This means that mu is equal to k over mu naught over 4 pi times 2. We also can solve that k is equal to 7.3 e to the -7. Knowing this equation and this value, we know that mu is equal to 3.65 a meter squared. In order to model what the magnetic field looks like in different places surrounding the magnetic bar, the following image was created using VPython. The different arrows shown show the magnetic field in different places, including 2 axial locations as well as 4 perpendicular locations to the magnetic bar. Because of these arrows, we are able to determine as well the 45-degree magnetic field at a distance that is X amount away from the magnetic bar. Knowing that, we were able to see that the magnetic field 45 degrees at distance d, which is equal to 0.2507, is equal to 1.15 e to the -5, in the x direction, 3.47 e to the -5 in the y direction, and 0 in the z direction. This was also calculated experimentally, and the two results will be compared. The data that was found during the experiment showed that the electric field 45 degrees away was -1.65 e to the -5, 4.3 e to the -5, and 3.93 e to the -5 Teslas. The modeling was very different, which was already shown and also is shown on this screen. And the reason for this is because the modeling was only taking into consideration the magnetic field of the magnetic bar. The difference with the data that was done experimentally is that with the Earth having a magnetic field of its own, we were not able to get purely just the magnetic field of the bar magnet. One way that we know that the data is skewed in the experiment is the fact that the z-value is not equal to 0 like it should be. A couple conclusion questions to consider are first, what if you had oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? If that had happened, the results would have differed much more because the magnetic field of the Earth would not have been as negligible as before. We would have been able to see this more so because we would have had a greater difference between the modeled data versus the experimental data. As well, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? First of all, the magnetic field and moment would increase due to there being double the magnetic force. As well, the distance that would be needed would also decrease because the magnet is more powerful. Thank you for listening. Have a great day.